Good morning everyone! Today I will continue to film my second video about ESP8266 traffic jams monitor. I will be covering soldering process, application build and configuring parts. So let's start with USB connector here. In order to solder micro USB connector properly, we have to use hot air soldering station and soldering paste. But I don't have any of that, so I will try to use technique with soldering iron instead. Firstly, you have to tin the biggest USB connector part. Then you have to append a bit of flux to the part again. And before moving to the next stage, you have to align and hold USB connector properly, so each pin should be aligned to corresponding part perfectly. Then we can apply heat to USB connector top side. Once connector is secured in place, you can solder individual pins. As usually, I would like to start with applying some flux here. Then I will try to touch each individual pin, and I have placed solder to my iron tip in advance here. Once fix is done, you can clean the connection and make visual inspection. As I can see, we don't have any issues here. But in order to make sure that all necessary pins are connected, we have to make proper testing using multimeter. In my case, I have connected 5 volts power bank here, and I will check whether this voltage is present on corresponding PCB pads. So, no connectivity issues here, we have 5 volts. You can notice here I'm using this high-tech tool. This helps me to hold all necessary components in place. It works by locking my tweezers on a specific position. And here we have our ESP8266. It will be responsible to convert USB 5 volts into 3.3 volts, which is suitable for our USB module. I will use this soldering technique over and over again, where the solder is applied to iron tip in advance, and sufficient amount of flux is applied to pads separately. This makes SMD Components soldering much easier, which is not the case while you are trying to solder through-hole components. And for the biggest part, I have to supply extra solder to make connection reliable and solid. Once ESP8266 is in place, we will switch to corresponding bypass capacitor soldering with few more resistors. Again, as I have mentioned before, technique used here is the same. You also can notice I'm using couple of pieces of toilet tissue here. This is just to do not damage PCB with sharp crocodile clips. Once all bypass capacitors are in place, we can make corresponding checks here, just to make sure we have stable 3.3 volts output from EMS chip. So we have exactly 3.3 volts, no issues here, and this output will drive our ESP8266 module. As the next step, we will solder our shift register, which will help us to convert serial signal from ESP module into suitable parallel signals, which will drive our LEDs. So we are using 74HC595 here. This SOIC16 SMD form factor is more convenient to solder if you are using drug soldering technique. And now we have the final touch here, just to make sure that our pins connections will be reliable. LED's soldering procedure at the same time is pretty much the same, so I will continue to use my tweezers here. Here we'll have two red color LEDs, just below a couple of yellow, and the rest will be green one. And here we have to pay extra attention on our current limiting resistors, particularly this set, which will be responsible to limit green color LED's current. So, in case if you will order two bright LEDs, you might use 2 kΩ or even 4 kΩ resistors to limit the current. Now we have all components soldered, and it's time to place our ESP module itself. So I'm using here my clothespin again. It helps me to hold ESP8266 in a position while I'll be soldering its parts. As usually, we have to solder one pin to keep it in place. Then we can remove this clip. The next will be diagonal pin, which will prevent any kind of rotation. And during this soldering procedure, you can think about what is the most convenient way to clean up all of this flux. In case of some types of flux, the basic dish cleaning liquid is fine, but in my case, with new type of flux here, I have found that glass and windows cleaning liquid is working more efficient here. This is where the main ingredient is spirit, and of course you always can use as a propanol alcohol. And here I will be using this key-type iron tip. This will help me to finalize soldering results, to make all connections reliable and shiny. In overall, this process of SMD Components soldering would take me much less time if I would have hot air soldering station and solder paste stencil. Now we have our ESP module in place and just few components left to solder. This includes UART receive transmit lines terminal, reset button and few jumpers. Then I would like to flash sample application. This will ignite LEDs sequentially, one by one. This is the same application which I have shown in my previous video. Here we have our final soldering results, and we are ready to flash sample testing application. This will help us to check whether all connections are soldered properly. To start flashing, we have to make sure to place jumper in the correct position. Once it is completed, we'll move it to execution mode. Now we have to use external USB to serial converter. This way it can be connected through USB port to our personal computer. So we have everything connected here, including our USB power supply line. And you can notice here everything is plugged into my laptop, which I will be using to flash our USB module. So here we have prepared our sample application, and you can notice it is exactly the same which I have shown in my previous video. And this is the method which is responsible to toggle our LEDs, taking ignited LEDs count as input argument. Now let's compile our application. No issues here. As the next step, we have to reset our ESP module. This will make it ready for application flashing. Now let's trigger our makefile target to start the flashing procedure. You can notice corresponding UART transmit and receive LED slides are ignited while writing this application. If you would like to know more details about how to program ESP module, you can watch my previous videos in this series. Verification step is done and we don't have any issues. It's time to move our jumper to execution mode. This way GPIO 0 pin will be pulled up to 3.3 volts and we can run our application. Let's switch on our module here. And as expected, our application works just fine. We have a sequence of ignited LEDs. This will conclude our hardware part implementation, and we can move forward to software part. Here I would like to start with Google Maps platform overview. This will allow us to extract all necessary information about traffic jams on a specific road. Also, I would like to point here that there is a free usage threshold on these services. So it will come for free for you, as long as you will be within limit of $200 on your REST API queries. This way, if you'll try to get traffic jams conditions every 10 minutes, then you will have about 5,000 queries per month, which will be within $200 free usage limit. I hope this promotion from Google will continue by that time you will be watching this video. Here we have to start to explore Directions API, and I will follow with this developer's guide. All links will be provided under this video description, so you could follow them to check how to create Google Cloud Console account, how to generate REST API security key, and other useful links. And here we have few examples describing how to query traffic congestion information. This will give us time in seconds, indicating how long will it take to drive from specific location A to some target destination B. The actual value which you will need to extract is described under this tag, and here you have to specify your API key, which can be generated through Cloud Console. As you can notice, everything works through REST API queries, so you can refer my second video in this series about ESP module. It describes how to query data from remote REST API service and how to parse result JSON message. Here I would like to notice about waypoints use. In general case, when you are trying to build specific road, it will try to propose few alternative options. This will create an ambiguity when we'll try to display congestion information using ESP LED bar. We will not know which exact road will be pre-selected. So, for these purposes, we can include extra waypoints, which will allow us to have some road pre-selected. And these are REST API parameters which needs to be used for waypoints definition. Also, we have to use this wire prefix against each waypoint. This will help us to avoid extra stopovers on our road. Let's try to compose sample HTTP GET query. I will be using curl command here, starting with URL base part. Then we can set departure time as now. This parameter will allow REST API to return current traffic jam conditions rather than using average statistics option. Then let's specify route origin point, intermediate waypoints to avoid ambiguities, and the final destination point. Please note that all commas, colons, and any other special characters needs to have proper URL encoding. As the last argument, you can set your API key. And that's it. Let's capture our HTTP response body. Here we are. We have the indication of how long will we drive through selected road, which takes the current traffic jams conditions into account. Then this value can be extracted, parsed, and used further to make prorate LED bar ignition, where all 8 ignited LEDs will notify us about long duration of staying in traffic jams, And as opposite, zero ignited LEDs can notify about absence of any traffic jams. Any other intermediate results we can present using linear interpolation approach, so we could have an overall sense in terms of what is happening on the road. Now you can see our application itself, and here we can set Wi-Fi connection parameters, which includes Wi-Fi session name and password. Here we can set directions API key, which can be received from your Google Console application. For more details about this key, please refer a link under this video description. Under this section, source, destination, and intermediate waypoints can be specified. Everything is represented as GPS coordinates. And here we have two integer numbers, which makes the definition when we should to ignite all LEDs. This is the case when time in traffic is more than worst road time parameter. Best road time, as opposite, will make a definition. How much will it take to drive this road without any traffic jams? This way we'll shut down all LEDs. In case of directions API, we'll predict time in traffic less than this value. All intermediate results will be calculated proportionally. This will establish how many LEDs will be ignited to display overall situation in respect of current traffic jams. And that's all in terms of what you need to change within this application in order to configure it under your selected road. Moving to our makefile, here you can notice we are using MBED TLS Library. This is because of standard buffer size to execute TLS handshake will not be sufficient to establish connection with directions API. This way we'll be adjusting TLS buffer size at this open source library. So you can find this library under native SDK folder. Within this root makefile, we want to switch configuration to release mode. Corresponding change we have to do within output build folder as well. And under this header file you can find buffer size definition, which is used for TLS handshake. We would like to increase this value to 9800 bytes here. This should be sufficient to establish secure connection with directions REST API. Then, under ESP build config file, we have to enable ESP8266 platform declarations. Library build process itself can be triggered using make-lib shell script. Here we just need to specify library name as input argument. And that's it. Our library is assembled and ready for use. As the next step, I will build our traffic jams monitor application. Here we'll use this extra declaration. This will allow to establish UART connection with the ESP module, which will help me to monitor debug logs while application will be running. So, compilation step is successful. Newly adjusted MBED TLS library is already included there, and we are ready to flash and test our application. Now firmware upload to ESP is completed, and we can make UART connection using Minicom. This way we can monitor debug messages. Once ready, we can click Reset button to start the application. Initially you will see red LED blinking. This will indicate that the application has been started, but traffic congestion information has not been downloaded yet. 1 minute later, REST API call will be executed, and corresponding traffic congestion level will be indicated. Today we have a bit of traffic jams on the highway due to road incident, so we are having level 5 here. And within debug logs you can find some useful information. Like here we have part of HTTP response body, indicating how many seconds approximately will it take to drive to destination point. I hope this device will be useful for you, so you could place it next to your alarm clock and always be aware about current highway congestion level. This way it will help to make a right decision whether to drive a car or take a train on a specific day. This will conclude our series about ESP8266 module. Thanks for watching this video. See you next time. Bye.